Hello. Hello. Can you hear me?
Yes.
Yes, sir.
Yes, sir.
Yeah. Hi.
Yes, sir.
Hi. Sorry, I will switch my video on because there's a light issue here. Yeah. So happy New Year. First of all, I hope you all your year started, all of your year started well. Uh, so last class, which was supposed to be on the 1st of January, did not happen because Anshuman wanted to take some extra class. Um, so we are one class behind. That's fine. So we can try to make up later on. So before I start, let me just tell you that I have uploaded up assignment 2 in the classroom just some time ago. The deadline is basically next week, and so that is good. So you can take a look at that. Of course, I will be discussing whatever I was asked, whatever you guys were asked to read up and all from last class, and something new stuffs today. Yeah, so there is another thing that I wanted to just have a talk to you guys. That is that in terms of the first assignment, I just again, I think I did it last time also, but is Ayush Chauhan here? Do anybody of you have any contact with Ayush Chauhan? Hello?
No, sir.
Is he a JRF or a master MTech student? You know that at least?
No, sir, we don't know. We have to look in the list.
You don't know. Okay, that's fine. So Ayush Chauhan is a JRF. So he is not there. Okay, fine, good. So he is, I think he's not attending this class. The other person that is we are looking at is Shubimoy Hatai. Is he in this course or something? Hello. Is he a Shubimoy Hatai is not a JRF student. So he must be an MTech student. Do you have any idea whether he is in this MTech course or not?
Sir, he is JRF.
Oh, he's JRF?
Yes, sir.
Okay, and he's he is not taking this course, is it?
Don't know about it.
No, it's a JRF. No, I'm not getting this list for here. Okay, fine, no problem. So these are the only two people who have not submitted the assignment. So that's what I wanted to verify whether what was the issue. Yeah. So I have not gone over the assignment 1 for you guys. I will go over it hopefully this week or so. Also, we will try to upload a model answer to the assignment 1, so that you guys have some idea about what to expect of what to write and all those kind of stuff. Okay, so that's good. Yeah. So okay, so now you guys tell me what all did you do in the last since the last class. Which all things did you manage to read? Any doubts, any questions?
Sir, I had a question in our
proof of the AMGM inequality using induction.
Right.
Sir, so one step that we wanted to show was that PK implies P2K. So that I understood, but so now when we wanted to show that PK implies PK minus 1,
Right.
so sir, you had in the last class, you said that in usually in such cases, we should start with an instance of PK minus 1 and then go about
No. Yeah, so it should not start with PK. So you should not consider this PK minus 1. Okay, so that's a, I mean, you should start with whatever you are going to prove. Yeah, in this case, it is PK minus 1.
Yeah, sir. So, but actually, in the proof,
Yeah.
we started with the we started by with PK, and I think then we went about proving PK minus 1.
In the writer, in the assignment that is in the thing that is there.
Yes,
Slide.
sir. Yeah, sir. Maybe I might have got it wrong, but I thought that's what
I think that should not be the case at all. I mean, then I'll be ashamed of myself if that is the case. Just one second. Let me. Just open this one. Maybe I can just share my screen. 1 second. Can you share me see my screen?
Yes, sir.
Yeah. So
you
all of these things are fine. You are not complaining about this part.
Yes.
You are complaining about.
Yeah, this is.
Yes. See,
So,
exactly. So what is it to prove? So what is K minus 1? PK minus 1 is what?
It's A1 plus A2 plus A3 by 3 greater than or equal to cube root.
Right. So this I start with this. Right. So I start with an instance of PK minus 1. Because this is what we want to prove. And then we say that, okay, we know that for anything is this true. This is not, I mean, this is what is the assumption. This is the assumption, right? So because we are assuming, but we start with this. So we have to prove this statement. This is what we have to prove. Okay, so A1, A2, A3 is not something that I have chosen. This is something that is given to us. It's an instance. You can think of it, an adversary has come in and given it to us. But okay, see what happens if A1 is this, A2 is this, and A3 is this, can you prove this statement? But then what we know is that if you take any 4 of them, any 4, doesn't matter, because we know that PK is true, right? So what we do is that we start with this A1, A2, A3. So this statement is something like for all things. So this is like, I mean, maybe if you wanted, I could have not had A1, A2, A3, A4. I could have had B1, B2, B3, B4 also. It's fine, because any positive B1, B2, B3, B4 will have B1 plus B2 plus B3 plus B4 by 4 is more than 4th root of B1 times B2 times B3 times B4. Right. So we started with A1, A2, A3. And then what we are doing is that we are doing that, okay, let's say B1 equals to A1, B2 equals to A2, B3 equals to A3, and B4 equals to A1 plus A2 plus A3 by 3. And then I am applying this kind of statement, this PK statement, on this set of A1, A2, A3, A4. See, the A4 is the one that I have constructed. You have given me, the adversary has given me A1, A2, A3, and the A4 is the one that we have started. We construct using the A1, A2, A3, A4. And then we go ahead. So this is what I meant, but you start with this instance. You cannot say that I am proving it for a particular A1, A2, A3. Somebody has given you A1, A2, A3, That is not in your hands.
Okay, sir. Got it. I misread it. Yes. Got it. Thank you, sir.
Okay. Yeah. So by the way, since you are talking about here, many people might be actually have thought that, oh, okay, see, I mean, this is a solution, but how did we? I mean, how can you think of this particular thing here? How why
Sir,
a4 equals to a, yeah?
Sir, the last line a1 plus a2 plus a3 divided by 3. I think it should be 3.
Yeah, it should be 3. That's true.
Sir, I had one question.
Yeah.
Sir, like, should it be A1, A2, A3, A4, A1, A2, A3 like that, or should it be in terms of K while writing?
In terms of K, so the general thing is of course not in A1, A2, A3, right?
Yes, sir.
So no, yeah. So general thing is, so this is just an example that was used for 3 things. What would be a general statement, right? So you have to prove it for PK, right? You have to work out for, so I mean, this is something that was expected. You guys will complete the proof actually for yourself. You want to say that PK implies PK minus 1, right? So what is it? So to prove, what is to prove that for, so basically it's a given, you can think of it, that given a1 to ak minus 1, prove that a1 plus a2 plus ak minus 1 by k minus 1 is bigger than a1 times a2 times ak minus 1 whole to the power 1 by k minus 1.
Okay.
Now, how do you prove it?
So similar way like that.
What is the similar way? What is the similar way?
Like, we know A1 plus A2 plus dot 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 plus A to the power K by K is greater than equal to
Yeah,
K
so
root of
yeah.
A1, A2.
So we know that for any B1 to BK, and all of them are positive, of course. So these are also positive. B1 plus till BK by K is more than B1 dot dot BK to the power 1 by K. Okay, so we have, this is what we want to prove, and this is what, so this is what we want to prove, and this is what we have. Now, what should we do next?
Let AK equal to A1 plus A2 plus dot 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 AK minus 1 by K. Sorry, K minus 1.
Right.
Then A1 plus A2 plus dot dot AK.
So the thing is that, okay, so let therefore B1 equals to A1, B2 equals to A2 till BK minus 1 equals to A minus K minus 1, and BK equals to A1 dot 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 A K minus 1 by K minus 1. And then you have to do some calculation. So then what do we know? Of course, we know this statement. And I again leave it to you guys to go and prove it. Just like here, right? We'll get that. Let me just quickly, how many of you actually have gone over this particular slide? I mean, I'm actually very curious. Okay, let me just quickly unshare it, and then I want to just hold on, just one second. It was 7, right? I mean, very important this one. Okay, so let me just kind of launch a thing. Please answer it honestly. Okay, so yeah. So what I am seeing is that so 7B hardly people have. I mean, so the huge number of people, 50% of people have not gone over it fully. Can you please, someone who has not gone over it fully, can you? I mean, are there doubts or are there questions or was it like obvious? Can you please tell me? I mean, like this is kind of again important. I mean, there are some people who have not gone over 7A, 7B, anything. So, I mean, because see again, as I told you, I mean, if you don't read this stuff by yourself, I mean, then my whole effort of uploading it is not helping at all. Okay, and if it is the case that okay, I have, I mean, I could not understand it, that's perfectly fine. Then you can just let me know what is it that you have problems and all. Hello. Hello. Are you guys hearing me? Is it audible? Am I audible?
Yes, sir, audible.
Yes,
I
sir.
was not speaking for some time and none of you have responded. So can I assume that you understood everything that has been done? Whoever did not read the whole thing, it was because they thought everything was easy.
Sir, in the 7B slide,
Yeah.
there were given induction for multiple parameters.
Right. That was
But we were not given any examples on it. So will you be giving us examples?
sure. I will do that. I will do examples on multiple parameters. I'll do it very soon. Yeah. Yeah.
Sir, in this
Yeah. Yeah. Go ahead.
in this particular problem, when you assign decay for a specific kind of value,
Yeah.
then it becomes a specific result. Is it a generalized thing?
See, I have proving what I want to prove is for general A, I mean for A1 to AK minus 1. That's what I want to prove. So this one you can put any A1 to AK minus 1 you want. Right? Only the AK that or BK that I end up putting is a special structure. But my goal was not to prove it for general A1 to AK. My goal was to prove it for A1 to AK minus 1.
Okay. I understand the point. Okay.
Right. What is it that we want to prove? That you should always clearly write, then you will understand what is going on.
In case of A1 to AK minus 1, I cannot assume any specific thing. But in
You
case
cannot.
of AK, I can assume it.
Yeah, you
Okay,
can
I
assume, because
understand.
that is not something that is. I mean, nobody
I-
told you anything.
Okay, I don't want to prove that. That is already proved. Okay, I understand the point.
Okay. So one question that can be asked is that where is it gone? Oh, sorry. I had another thing, right? Where did it disappear? Yeah. So, oh God, what happened to that one?
Yes, screen is not visible.
Hmm.
Screen is visible, but that board is not visible.
Yeah. No, not on the board thing. I was like more worried about this slide stuff that was there. This 7. What was it? 7B, right?
Slide is also not visible. It is something like an edit meeting poll.
So slide is not visible.
No, sir.
Nothing is visible.
So slide is not visible. It is showing some other page.
What is it showing now?
Some white page where some table type of thing is there.
Oh, God.
No, slide is displayed.
Slide is visible, sir. We can see slides.
Slide is visible,
And-
sir.
and-
AMGM
And
inequality.
it is 7B slide.
Yeah. Right now is open slide. Whoever could, whoever was not able to see this slide, can you see this slide now?
Half,
Sorry?
half, sir. Yeah, now it is.
Now
Now
it
it is
is
visible.
Okay, so maybe it is kind of some kind of buffering issue and all. Okay, so the thing that I want to say is that look at this one. Can somebody say that why was A4 chosen like this? Can somebody give me some idea of why was A4 chosen like this? Or in other words, more generally, why did we choose BK to be of this form? What was the intuition behind it?
Sir, if we add a mean means by say we have k numbers, k minus 1 numbers, and we want to calculate the mean.
Yes.
If we add another mean to it, then mean will not change.
Exactly, very good point. Right, exactly, that is the idea. See, this is some quantity, right? This is the mean of the k minus 1 numbers, right? So what we wanted to do is that, okay, I want to add another number and take a mean. Okay, so I will basically do B1 to Bk and take the k. So the average of k numbers, but the k minus 1 numbers are given to us. Another number such that the value doesn't change. And the way to do it is that if you add a number which is exactly the mean value, then the mean of the whole structure or whole set doesn't change. Now this is something that is, I mean, like say if you have in a class, you have, I come and say that, oh, see, on an average, all of you have got in the assignment 1 76 marks. Okay, very good. Now, but I have not, say somebody else then comes and says, oh, you have not corrected my assignment at all. Okay, fine, I correct it and I say, okay, your mean still doesn't change in the whole class. When can that happen? That can happen that when the average, when that person that he or she has got in the assignment that I have not corrected or that was added later on is exactly the mean of the previous one. So that's why when we kind of wrote this statement, I don't know whether how many of you kind of verified it or not, but this statement, this A1 plus A2 plus A3 plus A4 by 4 is actually A1 plus A2 plus A3 by 3. This, if you try to prove it by yourself, it's a bit of a ugly calculation. You have to do multiply, do some stuff and subtraction and all. But intuitively, this is obvious. this statement. I am adding another number. So this is a mean of 4 numbers. This is a mean of 3 numbers, right? And all I'm doing is that I'm adding a 4th number to these 3 numbers, which is actually the mean of itself. So this statement that is there is an automatic statement. You don't have to do a lot of calculation on. And so by doing so, what happens is that the left hand side remains same. Oh, by the way, somebody was pointing out that this should have been 3. Not only this has to be 3, something else had to be 3 or 4 also. This one should have been, yeah. So this is actually correct. No, it's okay. So this is actually A1 plus A2 plus A3 by plus A4 by 4, which is equals to A1 plus A2 plus A3 by 3, which is more than this one. So there is a kind of step jump over here. So is it clear why this one was done? Okay. I'm assuming that 0 answer means yes. Any other comment? Yeah.
Yes, sir. I have sir, one doubt, sir. Sir, how we select such numbers that it is how can we select all those things that it's true for this inequality, sir? For any particular problem, sir? Sir, actually that I've understood all the proofs that is given, but how we actually if some new problem is given to us, then how do we proceed?
Yeah, so it is, so that is not, see, there is no thumb rule. Okay, so that is exactly what I'm saying. So there is no thumb rule. You have to come up with some ideas. It is your creative idea. But see here particularly, just think of it that you had this statement and you had to prove this statement, right? So how would you have thought about it? Like one option is that, okay, of course I have A1, A2, A3, these 3 are maybe the 3 same things, and the A4 I have to put some value. Maybe I can put A4 equals to 0. If I put A4 equals to 0, then first of all, it's not very useful because then this part becomes 0, and secondly, this is just A1 plus A2 plus A3 by 4. I want it to be A1 plus A2 plus A3 by 3. So in some sense, it says that if you put, what kind of A4 can you put so that this quantity on the left hand side, right, this thing, this whole thing can be equal to this thing, right? So note that this is what you have and this is what you want to prove. So one option, obvious option is A4 is some fixed to something so that I will be able to get this result. So a standard technique would have been to put, I mean, a natural one is to put, okay, let's put A4 equals to A1 plus A2 plus A3 by 3, then the left hand side becomes what we want. Of course, the right hand side is something else, but then once you do the calculation, you realize that, oh, this works out. So that is what I'm trying to say, that particular for this problem, there is an intuition behind why A4 was chosen like that. Different problems will have different techniques. There is no something like, oh, this has to be like done this way, and or this is the idea. But in this particular case, you can do you can have some idea about what was being done, right?
Okay, sir. Okay.
So any other questions that you have? Any comments? Okay. So if not,
Sir, the A4 will be here. The A4 is selected, which is the mean of the previous one.
Exactly.
So that the average will not be changed.
The average will not change. Yes.
Okay.
Yes, that is the exact reason why A4 is chosen like that.
Sir, I had a clarification. On the 13th slide, can you scroll up to?
In this one only?
Yeah, yeah, yeah.
Okay, now I don't know which is certain state. Can you just tell me when to stop?
Okay, sure.
Somewhere here,
No, no, no.
back.
Yeah, yeah, back. Yeah, this that proposition. So here you have written that that is P1 or that thing. So
No, no, yeah, yeah, yeah. It is not or. It's and. We had a discussion about this last time. It was a mistake that was there.
Yeah, yeah, cool.
Pointed out. This was P1 and it has to be.
Sir, in this slide, I have also a question. For
Yeah.
all k or there exists a k?
No. This is for all k. So what happens here? What is this mathematical induction statement says that if you prove P1 and for any k you can prove that Pk implies Pk plus 1.
But
Then
basically,
that implies that for all k bigger than 1, then you have Pk.
in the right hand side for all k, I understand it. But we assume for a particular k it is true. So then is it for all or there exists a
No,
k?
see, no, not there exist. Okay, so what happens if you this one? What if this is there exist? Okay, then what did this statement say? This will say that okay, your P1 is true, and there is a thing maybe P10 implies P11. That's it. Right? P1 is true and P10 implies P11. From that, can you deduce? Can you hope to deduce that for all k P1 is Pk is true?
Okay, I understand.
Right? That's cannot be right. So it is for all k greater than 1, you have to Pk implies Pk plus 1. Now, when you prove this statement, that's a different issue. So this is the induction hypothesis, right? When you prove this statement, you mean that okay, fix the k and then prove that it Pk plus 1 is true. To prove that you have such a statement, this is what we prove by induction hypothesis. Means you have to end up proving this statement. You have to proving this statement, and then automatically by the principle of induction, mathematical induction, it will imply this statement. Yeah. Any other questions?
Sir, 7th A slide recurrence question.
Recurrence question. Can you just say where it is?
7th A slide.
7A slide. Acha. Just 1 second. 7A. Can you tell me where was it?
Yes, sir.
One later.
Yes, sir.
Is this one, right? Yeah.
Yes, sir.
Yeah, tell me.
Sir, in this question, I am not getting it for the k and k plus 1. That how we are tackling that.
How we are tackling that? Oh, how we are proving that?
Like I'm not getting the approach.
Okay. So what does this approach will say, right? So forget this thing. Let me give you a slightly simpler one. That might be easier. Okay. So say I have something of this form. That yeah. Say if T of n equals to 2t n over 2 plus n, okay, say absolute, then t of n is less than say 100 n log n. How will you prove this statement?
Sir, I will I will solve it for t of n by 2, and I will see that how the recurrence is breaking into the sub problems, and then I will finally do it for some positive k. And
Okay. So
if the tree will be symmetric.
Okay, so
then
that
I
is
will,
one way of doing it for here, okay? But when we are doing for induction, okay, a simple way to do for induction is to say that, okay, let it be true for, so I know, say so this is statement, say Pn, okay? So this whole thing is Pn, okay? And I want to prove what? For all n greater than or equal to 1, say, okay, and let's assume that t1 equals to 1 or something like that. Okay, for all n greater than or equal to 1, Pn is true. This is what we have to prove. Okay, so one way of doing it, so one way is what you were saying, which is basically unfolding this whole stuff and writing a recurrent, I mean kind of, okay, t of n equals to 2t n over 2 plus n, then I can write it as 4n, 4 something like 4 times n over 4 plus something, and so on and so forth. But the another way of doing it is not to do it like that, but to do it directly from induction, in which first see what we have to prove. What we have to prove is this statement, right? This is all we have to prove. So first thing that you prove is, of course, the base case. I am not proving that at this point, and we can prove it. Secondly, a standard thing here is that the induction hypothesis. What is the induction hypothesis? So let Pk be true for any k, or Pi be true for any I less than or equal to k. And then what do we have to prove? I have to prove that the inductive step is that, so that means from, I know what? I know P1, P2 till Pk. I want to prove that after I know all of this thing, from this can I end up proving Pk plus 1. Okay. Now, is this clear? At least, I mean, like, I have not done anything. I have formally written down what is it that we need to prove. Hello, is it clear? Or are you confused already?
Yes, sir. Yes, sir.
I mean, you are following it, right?
Yes, sir.
Okay, good. So now, what do you have to prove? I mean, almost blindly you can do this one. Okay, that I told you that you start from Pk plus 1. What you have to prove, you have to prove. So what do you have to prove? To prove what? To prove that T of, so this is what we have to prove, right? Oh, sorry, I made a mistake over here. This is not what this Pk is. Pk is actually just this part. So this part is Pk. This is Pn. And this is a property of the, this is just a property of this Tns. So this is, so this one, so if I maybe make this one bigger, this is P of n. Okay, the red part is P of n, and this is what we have to prove, that for all n bigger than or equal to n, T of n is less than 100 n log n, right? So what do we have to prove? We have to prove that T of k plus 1 is less than 100 into k plus 1 log k plus 1. Okay, yeah, I don't know how to prove that, but I know that there is this particular stuff. The property of Tn, this has nothing to do with Pn and all, right? So that means I know that T of k plus 1 equals to twice T k plus 1 by 2 plus k plus 1, right?
Yes, sir.
Now this quantity, do we know anything about this quantity? Of course we know, because we wrote that P of k plus 1 by 2, k plus 1 by 2 is somewhere here, right? Because k plus 1 by 2,
Right, sir.
since k plus 1 by 2 is strictly less than k plus 1, or so I know that T of k plus 1 by 2, and this is by induction hypothesis, right? This is where this hypothesis is there, this induction hypothesis. This is less than 100 k plus 1 by 2 times log of something, right? K plus 1 by 2 or something. So all that we have to prove. Okay, so this is something we know, right? This is we know. So what do we have to prove, or enough to prove? Not go back always to see what you have to prove. So I have to prove this statement, right? Now I have to prove this statement, and I know that this one is equal to this one, and this one is less than this quantity, right? So we know that. So okay, maybe I should write it, not forget before I prove enough to prove. So let me write it down. So we know by induction hypothesis, T of k plus 1 is less than or equal to 2 times T, this quantity, which is equal to, which is less than this. So 2 times 100 k plus 1 by 2 times log k plus 1 by 2 plus k plus 1, right? It's from here, from this statement I'm getting this. We know this by induction hypothesis, and so all that I have to prove is what is enough to prove. So enough to show. So see, this is what I had to prove, this is what I have ended up proving. So enough to prove that this quantity is less than this quantity, right? So enough to prove,
Right.
prove that this quantity, whatever this 2 times 100 k plus 1 by 2 log of k plus 1 by 2 plus k plus 1 is less than what, 100 k plus 1 log k plus 1. And this is just a plain manipulation, right? This is just a simple manipulation that you have to. So this is what you do for recurrence always. Same thing over here. So you have to prove this, right? So what is a PK? PK is that. So actually forget PK. I mean, actually it is written in a slightly complicated way. Think of this one. PK is actually this quantity. AK equals to 2 to the power k plus 3 to the power k. Okay, this is what we know. Now we know that this statement is true. That is what our induction hypothesis. So we have these two base cases that you do, B1 and B2. And then you do have the induction hypothesis that let it be true for some particular k and k plus 1. Then can we end up proving it for using this k and k plus 1? We have to prove it for k plus 2. And how do you do it? So you start with the instance of pk plus 2, right? And yeah, maybe I don't want to go over it line by line here, but you start with the instance of pk plus 2. Now you know that pk plus 2, what is that pk plus 2? Pk plus 2 is basically that ak plus 2 is equals to 2 to the power k plus 2 plus 3 to the power k by 2, k plus 2. And we know that a to the power k plus 2 can be written up in this way into the smaller statements of forms of ak plus 1 and ak, right? And we know as the upper bound of ak and ak minus 1, ak plus 1 over like this using the induction hypothesis. And so you kind of write it and you will get it from there. Is it clear?
Yes, sir. Thank you. Thank you very much.
Hello.
Yeah, hi.
Sir, there are some versions are given in the for the induction proof. So there may be more versions
Yes,
for this.
there are lots of versions, the infinite number of versions.
Can you use any?
You can do any of that.
Okay, sir.
Yeah.
Okay, sir.
Infinite number of versions, you can do any one of them. Yeah, as I told you, that version, as all that you have to, I mean, ensure that this or the set that you want to prove for everything works out. Yeah. Any other questions, doubts, questions? Yeah. Okay. So if not, I wanted to actually start into this induction on combinatorial objects, something that we have not done yet. Okay. So I start with actually, we call it induction on graphs, but this problem. Do you remember this problem? So there are 2n participants in a party, and basically people shake hand with each other. But if any, I mean, if there's no 3 people who shake a hand with all of them. So in other words, if you consider the participants as vertices, and we had gone over this one earlier. If all the participants are vertices and the edges corresponds to whether 2 participants have shaken hand with each other or not, then it basically says that there is no triangle in that graph. And the thing is that you have to prove that if there are no triangles in this graph of 2n vertices, then the maximum number of edges that can be there is n squared. Are you all comfortable with this particular problem? Did anybody of you try to solve it? So nobody tried to solve it at all? Okay. So none of you have tried to solve it. Excellent.
Sir, I have tried it,
Yeah.
but I was stuck at some point.
Okay, but you have tried it. Okay.
Yes, it was some, I think it was related to some Hamiltonian graph, some concept. I was stuck at that point.
Okay, I mean, okay, fine. Okay, what about others?
Sir, I also tried the problem. I made a tree. I made a tree from the graph, and then I kept adding edges so that there are no triangles. But I'm not able to complete the proof. The last part I still need to work on a little bit.
Okay. Okay. So see, there might be other ways of solving it. Okay, but what I'm going to give you now is a proof by induction. Okay. And this is something that I mean, usually in my other discrete math classes, I just tell students that at some point of time, if I ask you, can you suggest a problem, I suggest a way of solving it, And in case you are sleeping in the class, you should just wake up and say induction. The induction is basically the most powerful proof technique that we have. And that should always hit your mind first. How do you prove it? Induction, always. Okay. So here, see, there is a natural thing to induct on. But before I start going to the induction part, let's think about what is going on. So I have this graph, right? And I have some vertices over here. And I have some edges like this, like this. Some kind of stuff like that, right? And there is no triangles. Like this graph doesn't have any triangles. It might have odd cycles, no problem. So what we want to prove is that this one has number of vertices is twice n. And we want to show what? The number of edges is less than n square. Okay, so basically it is a triangle free graph.
Sir, can you please repeat once? My connection went off.
Yeah, I mean, from when did you lose it, me?
What is this graph that you have just drawn?
So this is some graph which is triangle free.
Oh, okay.
This is some triangle free graph. Okay, I'm just trying to see how one can approach this whole stuff. Okay, it's a triangle free graph, and I have the number of vertices is twice n. And we want to show that the number of edges is less than n square. This is what we want to show.
Okay, sir.
So if you have to do induction, right, you can always, I mean, of course, the main hardest part most of the time is the inductive step, right? Which basically means that you have to kind of reduce the problem, right? Unless you do some backward induction and all those kind of stuff. But most of the time it goes from pk implies pk plus 1 or pk implies pk plus 2 or some kind of stuff like that, right? So you have to reduce the problem. So you start from a pk plus 2 or in this way. So a graph on 2n vertices. And can I somehow produce another graph on a slightly less number of vertices, which is also triangle free? Okay. But when I have it on the triangle free, of course, I will lose some edges. I have to calculate that. So one way is that, okay, why don't we just take two vertices? Say I have these two vertices. If I just remove these two vertices, what happens? I have these two vertices, I remove them, and the rest of the graph, which is basically this rest of the graph, is a graph on 2n minus 2 vertices. And of course, this is triangle free. So the number of edges within this graph, so I have a G, I started with a graph G on 2n vertices, right? I picked up U and V from the vertex set of G, and I considered G minus UV. So let's call this one G prime. Now what is G prime? G prime has the number of vertex, for how many vertices are there? It is 2 times n minus 2. Fine. What is it? G prime is also triangle free. Because G was triangle free. If you remove some edges or some vertices, it still remains triangle free. And in some sense, I have produced a smaller triangle free number of graphs. So I can hope maybe to apply an induction hypothesis on that. Okay, so hope. So let me write it in terms of different color, that I can hope by induction hypothesis, the number of edges in G prime, this is bounded by, sorry, not n minus, you guys are really not paying attention. N minus what?
Yeah, n minus 1.
Sir, it is 2n minus 2.
2n minus 2, yeah. By induction hypothesis, I can hope to prove that number of edges is less than n minus 1 whole square. Excellent. But see, this is not our thing. This is what we can assume, right? But our goal is what? What is our goal? Let's not forget the goal at any point of time. Goal is to prove that G is less than n square. So there are this number of edges. So these are the edges that are here within this, maybe this chunk. Other than that, there are some other edges that we have not counted, right? Like the edges like this. How many edges can there be like this? How many edges can there be? So there are two kind of edges, right? There are the edges here. So note that the edges, total number of edges within this set. Okay, I mean, I don't want to. This edges is upper bounded by n minus 1 whole square, and then there are edges like this. So the what we call is that, so edges of this graph is actually edges of G prime disjoint union edges of what? U to rest of the graph, right? U to G prime, edges between U and the vertex set of G prime, and edges between V and vertex set of G prime, right? So this set of graphs, these graphs. How many edges can be there? Can you upper bound something?
4 into n minus 1.
Huh?
2 into n minus 1.
Why 2 into n minus 1?
4 into n minus 1.
Why?
Because out of the 2n vertices, 2 are out. So 2 into n minus 1 is left. And from each vertex, we can have 2 into n minus 1 edges. So there are 2 vertices. So 4 into n minus 1.
Okay, so you are saying that this edges over here going out from U, this can be at most, there are 2n minus, so their total number of edges, no, number of vertices over here is 2 into n minus 1. So 2 to n minus 1 possible edges can there be. Similarly, here also there can be 2 into n minus 1 edges, right? So,
yes.
So by the way, I have forgotten to add one more edge over here. Edge UV, right? So this quantity, okay, so what do we have? This quantity is less than n squared, n minus 1 whole square. This quantity is less than 2 into n minus 1. This quantity is less than 2 into n minus 1. And this quantity is less than 1. So this whole thing, the total edge set of the graph is less than n minus 1 whole square plus 4 into n minus 1 plus 1. The problem is that you realize that this one is too much. This is not less than n square. We were hoping to prove that this is less than n square, right? This is our goal. This quantity is not less than n square. I mean, I can even do the calculation completely, right? This is equals to n square plus 2n plus 1 right? Plus, minus 3 or something. I think it will come. So this will become n plus 1 whole square minus 3, but we wanted it to be n square. Okay, so this didn't work somehow. But can we do something?
Here, one thing will happen if I join a vertex with V, then I cannot join that vertex with U. That
Why?
will
Why?
that will form a triangle.
Why?
Form a triangle.
Because U and V is connected itself.
If U and V are connected.
Yeah, and we are taking that U and V is connected in the last disjoint union.
No, we are not. I mean, that is the maximum one that we told.
Okay.
But you made a very good point that if, now this is a big if, okay, if there is an edge between U and V in the edge set of the graph, so there is an edge, then what happens? Think here, there is an edge between U and V. Then if U is connected to this vertex, can V be connected to this vertex?
No, sir.
No, sir.
If it is connected, then it becomes a triangle. And we know it's a triangle free graph. Right? So in that case, if U and V exist, then how many number of, what is the sum of the degrees of U plus V? So any vertex here, basically this 2 into n minus 1 number of vertices here, right? They can either be neighbors of U or neighbors of V or none, but it cannot be that it is neighbors of both. Is this argument clear?
So, sir, the total degree will be 2 into n minus 1.
Exactly. So total degree cannot be more than 2 into n minus 1. Right?
Yes, because otherwise it will form a triangle.
So this plus this together, therefore, will become 2 into 1 plus 1. So if this is the case, then U2 vertex set of G prime plus H2 vertex set of G prime, this is less than 2 into n plus minus 1. Right? But this is not that this is particularly if this is the case. But in that case, are we done? Let's see. This is n minus 1 whole square. This is 2. This one we have now got a separate one, and this is 1. In that case, how much will edge of G comes out to be? It is upper bounded by n minus 1 whole square. So this is because of the edge of G prime, plus 2 into n minus 1. This is the edge. This is this, right? Plus 1. What is this number?
N squared.
Wow, this is n squared.
N squared.
So this is exactly the proof. See, we have not done induction yet. I mean, we have done induction, but in a bit of how we have kind of found out the proof of it. So how should it happen? So let us write down the proof exactly. Okay. So see, what is the base case? I am not proving the base case once again. Okay, so you prove the base case. Base case is the pk for k equals to, or pn. Oh, first of all, induct on what? We will first induct on n. So prove that for bk for k equals to 1 and 2. Maybe less. I think 1 is good enough. Okay, p equals to 1. Now, what is the induction hypothesis? So induction hypothesis is that let pk be true for all k less than or equal to n. What does it mean? It means that what is pk? Maybe I should write down pk. It means that any graph on any triangle free graph on 2 times k vertices has at most k square number of edges. And let's say, okay, maybe just to make our life slightly simple, let's say that we assume that this is true for all k strictly less than n. Okay, and so in the inductive step, what do we have to prove? To prove p of n. Okay, so what does it mean? So let G be a graph on 2n, we are triangle free graph on 2n vertices. So pick an edge in G. Say pick an edge, let's call this one UV in G. Then consider G minus UV. Note that now I'm not picking up anything, I picked up an edge because this was important, right? U and V must be connected. Someone must have an edge between them, right? So consider G minus UV and let's call this one G prime.
Sir,
yeah,
we have taken base case as 1. So if we just remove U and V, it will be a null graph.
No. Base case has 1. So base case is, you don't prove base case using this technique, right? So base case is what? K equals to 1.
Yes.
Means the total graph on 2 vertices.
Correct.
Can graph on 2 vertices be a triangle? A triangle, how many edges can there be for a graph on 2 vertices?
There can be only one edge.
One edge. So which is less than 1 square. So
But
base
now
case is correct.
Base case is correct. Now we are inducting on the base case. So we are removing 2
Then we are
nodes from
starting
that.
from what? No, induct, not induct. We are trying. Next step is what?
Next step, we are assuming that it is true for 2 into n, 2 into k.
2 into k, right? So, like if you go step by step, I know that k equals to 1, we have it correct. Next thing would be, do I know for k equals to 2?
No, but we are proving it for k minus 1, right? We are removing 2 graphs, 2 nodes.
So I want to prove it for Pn.
Achha.
Right? So I have done it for P1. That's base case done. The next thing that I need to prove is P2.
Okay.
Okay, I start from something. So K is what? So by the way, maybe this is what maybe making it. Proof for Pk, K is greater than or equal to 2. See, Kn equals to 1 is kind of done, right? That's the base case.
Yes.
That is done separately. So I start with P of n for n greater than or equal to 2. Some n, I don't care what is n.
Okay.
Okay.
Then we'll remove a lesser number of nodes. It will be true. So okay.
Yes.
Okay, sir.
Now we will remove. Right? So what is G prime? What is the G prime's property? Let's say G prime's property. The number of vertices in G prime is, of course, 2 times n minus 1. Right? Good. It is triangle free. So by P of n minus 1, which is something we have assumed by the induction hypothesis, right? Number of edges in G prime is less than how much? n minus 1 square. And then you kind of do the whole thing how we did, right? So now edges of G is equals to edges of G prime, disjoint union, edges of U with the vertex of G prime, disjoint union, edges of V, G prime plus union UV, right? And you say that since UV is an edge in G, so if UW is an edge, implies W phi is not an edge. So E of U G prime union E of V G prime is less than or equal to 2 times n minus 1, which means that, or hence, edge of G is less than size of G prime plus 2 times n minus 1 plus 1, right? Which is less than n minus 1 whole square plus 2 n plus n minus 1 plus 1, and this is by induction hypothesis, which is equal to n. So we started with a graph on n to n vertices, okay, and then we chose a correct way. It's very important. This is very interesting actually. We just did not take a smaller graph, but the smaller graph that we worked on was specially chosen. It was chosen such that the edge exists, and then I choose that edge. If you don't assume this particular property, if you don't use this thing, then you cannot say something like this. Right? So the whole thing is to start with a Pn, a big graph on n vertices, on 2n vertices or whatever that kind of stuff is, and you massage it to choose the right smaller graph and then work on that. It is clear? Hello.
Yes, sir.
What about the rest of you?
Yes, sir.
Yes, sir.
Okay. Sir. So if it is clear, so I am going to, so I think I will not go for too long today. I have some more problems that are here, okay? I want you guys to think about them, and then next class I can discuss it again. One of them I have spoken about is the tournament problem earlier. Here also try to prove it by induction. And then this is another thing called an ANSYS problem. I don't want to kind of go over these problems at this time. Okay. But I want you to think about it, how to prove it. And I will upload this.
So what is this capital R?
Whatever, it is a function. Capital is just a function. The function that takes two values, P and Q, is written there. It's a number R, PQ is defined as the smallest integer n. So that among n people there exist. So don't worry about reading it right now. I will upload it, and your job will be tomorrow, day after tomorrow, and all to read these two things, problems, try to solve them. Okay, and we can discuss them in the class. By the way, this I think one of them at least, or even this handshake problem is also there in your assignment. I've given it so that you learn, I mean, you know how to write or what to write. Okay, I want to check it that you know how to write. But basically the idea is all that whatever was done just now. Okay, if you understood how it was done, you will understand it. Of course the tricks are different, but high level picture they're same. Okay, so if there's some questions I can handle now. If not, I will now go and give you two very interesting problems for you, which you have to just think right now. Okay, first one is this problem. Oh, by the way, is there any questions, doubts, clarification that I need to make?
We will not prove for the case if UV doesn't contain an edge.
Ah, very good point. Oh, what happens if, okay, so see, I don't care about UV contains an edge or not. I started with a graph G, right? Again, like in the case of the AMGM, my job is to prove it for a graph G. What is the G prime coming up? G prime is up to me. As long as I am able to prove for this H set of G, I am done. Right? And that's what I have ended up proving. Now, the only thing that you might say is that, oh, see, you have chosen an edge in UV in the graph G. What happens if you have chosen a UV which is not an edge? Who cares? My job is not to go and prove that. My job is to prove this. My job is to prove this statement. That what is the proof, right? My job is to prove P of n, that the H set of G is less than n square. Right? So I have intentionally chosen an edge, UV, which has an edge. If I choose an UV which doesn't have an edge, then what happens? Then yeah, my argument would not have gone through. I would have not been able to prove it. See, when somebody asks you to prove a solution, prove a problem, right? You prove it. Nobody asks you things like, why didn't you prove it like that? Or why didn't you show that way we will not be able to prove it? That is not the goal. Your job is to prove something. You can take any path you want. As long as you prove it correctly at the end, you are done. So here also that is the case. My prob was to prove this one, that H set of G is n square at most. So I chose an UV such that there is an edge, and then I did everything in the through this lens of G prime, and then I managed to ended up proving. At the end, what did we prove? That edge of G, or this is less than n square, and this is basically of the final result, that all that matters. That is what that matters, right? Now the only thing that you can ask is, what happens if there is no such edge in G? I told you to pick an edge, UV. What happens if G doesn't have any edge? Then what happens?
Then there is nothing to prove, since 0 is already less equals to n square.
Exactly. Then there is nothing to prove. So this case I have not written up explicitly, but basically if there is no edge in G, then P of n is vacuously true for this case G. Right? Is this clear, or is there confusion there about picking up this edge UV?
Yes, sir, it is clear.
It is clear, right? Yeah, I mean, I don't think you guys have seen this kind of induction before earlier, or most of you have not seen it. So this is what we call combinatorial induction, and this is something that we will need a lot in our course. Okay. Yeah. Okay. Any other questions? Okay. So if not, so in the slides, I have two statements. Okay. First statement is this. Do you think this statement is true? Every graph with more than 3 vertices and minimum degree 2 contains a 3 cycle.
No, not true.
Oh, not true.
No, sir.
Oh, why not true?
Because we can take a square. Where
Exactly.
notes.
We can take a square, and that square has 4 cycles, 4 vertices, right? Something like this. I can try to. So, yeah. There are 4 vertices. Minimum degree is 2, right? And it doesn't have a triangle. So this statement is not true. But I've given you a proof of it. Okay. I want you to go and read it by yourself carefully and see where is the problem with it. Okay. I want you to, I'm not doing it here because I want you, all of you, to independently do it. I don't want it to, of course, I will discuss it in next class. Okay. So your job is basically to read, to try to solve tournament problem, the Ramsey's problem, and try to understand why this proof is not right. And I have another statement. The statement says that all cows are of the same color. Do you think this statement is true?
No, sir.
No, right? Okay, I hope that was clear. Since you guys are not answering, I was like doubtful whether you accepted this statement or not. But this also has a proof. Okay? A proof by induction. Your job will to think of these problems or statements and find out a mistake, where the mistake is. Okay. Good. So I think I will stop here. So this is what you have to do. I will upload them in the class, in this place. Your job will be to read the handshake, this, try to solve these two problems and solve these two problems, or not solve, but identify the problems in these two cases. Okay. Please, I mean, I can only insist that all of you to try them by yourselves, because if you are not understanding this problems, then you will struggle for the rest of the course like anything, because almost certainly almost the 90% of the course is basically on induction techniques on such objects. Okay. Induction should become a very standard simple statement for you guys. Okay. Good. So any other things? Any other statements, comments? Okay, so if not, let's stop now. We can do it. Yeah, we'll meet again on Friday, right? Yeah. Okay. Bye.